Hello, in this video we're going to look at finding the center of mass. We're going to begin with one dimension so that in the next video we can extend to 2 and 3 dimensions. So let's start with a very simple case where the answer is actually completely obvious, but use this to build up a more general formula for finding center of mass. So let's consider just having two particles with the same mass sitting somewhere in our coordinate system. So we'll have our y-axis, which we don't really need, and our x-axis. And sitting on there we have particle 1, we'll say at position x1 and we'll give it mass m, and we'll have particle 2 at position x2 with mass m, and we want to find the center of mass. Now we know the center of mass can't be to the left of both particles or can't be to the right of both particles, but it would have to be in the middle. So the center of mass is the center of this whole thing's mass. So in this case it would trivially be right in the middle. Since both have the same mass, of course the center is going to be halfway in between. So let's write that out anyway. So the center of mass is equal to the location x1 plus location x2 divided by 2. This would put our center of mass right in the middle. And what we've done here is we found the average. Or specifically the average of the x-coordinate. Okay, so that's for two particles with the same mass. Let's try something similar. Let's do many particles. Still all with the same mass. Then the center of mass would be located again at the average location. It would be at x1 plus x2 plus x3 plus however many x's you have, divided by the total number. We'll call that capital N. Or we could write that in shorthand using summation notation as 1 divided by n times the summation. We'll use index I going from 1 to capital N of xi. Okay, so this is still the average. And if you're not familiar with this notation, you've probably seen this in calculus. What it means is add up all the values here where we have I be 1, then 2, then 3. So this is x1 plus x2 plus x3 plus dot 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 all the way up to x capital N. And we divide that whole thing by 1 on n. So it means exactly the same thing, it's just a little smaller for writing. Now here's a question. What happens if the masses aren't the same? How would we handle that? Because we haven't included mass anywhere in our average. In fact, what has happened is the mass has canceled out. Now, if we think about this, we want particles with bigger masses to count for more and particles with less mass to count for less. Okay, so we want our average here to be weighted by the mass. Now, I don't mean weight in the sense of mass and weight. I mean weight as in how important each factor is. So what we want now is that our x center of mass, instead of just being a arithmetic average, is going to be a mass-weighted average. Okay, so for two particles, the way that would look is we would take mass 1 times x1 and we would add that onto mass 2 times x2, and we would divide not by 2 but by the sum m1 plus m2. So in this case m1 and m2 are the weights. Okay, and so imagine, let's say m1 was 1 billion and m2 was 1, just to have some extreme case here. In that case, this first term is going to be huge compared to the other term, and so this has a much bigger weight. It has a much bigger effect on the average. Alright, so then we can finish this off just by generalizing to have many particles with weighted averages, in which case our center of mass is equal to 1 divided by the total mass, instead of the total number, the total mass, and then we'll sum up with our index I going from 1 to the total number of particles, mi times xi. where we're going to define capital M as simply the total mass. So that would be adding up all the masses. Okay, so let's go and put a box around that. So keep in mind, this notation is just a little bit more compact compared to what we have up here. Normally, if we're going to do this by hand, we might have 2, 3 masses. There are other tricks we would use if we have 1,000 masses. We, in reality, would not add up 1,000 terms in our calculator. That would be crazy. But we'll talk about that in a later video. Before we do that, let's try an example where we'll have just 2 particles. I'm going to pause the video for just a moment. I'm going to write down the example, and I'll be right back. Okay, so our question here gives us 2 particles. The first particle has mass m, and it's located a distance L from a second particle with twice as much mass. And we want to find the center of mass of these 2 particles relative to the first. Now the real key here for calculating the center of mass is to be smart with your coordinates. We can put our origin anywhere we want, and a good place to put the origin is on top of one of the particles. Okay, and the reason for that is that it'll make it a much simpler expression. So let's put the first particle at the origin, x equals 0, and that'll be our first particle. And then our second particle would be somewhere on the x-axis, a distance L away. So this would be distance L, and we had mass 2m. And we can guess that the center of mass is going to, of course, be somewhere in between, closer to the more massive particle and further from the less massive, so somewhere over here would be our center of mass. Okay, now if we wanted to calculate exactly where it's going to be, we would use m1 times x1 plus m2 times x2 divided by m1 plus m2. Now remember, we put x1 at the origin, and I said that that's a good thing to do. Well, if we think about what's going to happen right here, that means x1 is equal to 0. So our first term is 0, so we don't really have to worry about that. Our second term is going to be equal to 2m, because m2 is equal to 2m, times capital L. And then we divide that by the sum of masses. So that would be m plus 2m, or 3m. So our fraction here simplifies to 2ml divided by 3m. The masses would cancel out, and the location of the center of mass is equal to 2/3 the total length. And so, sure, that's definitely closer to the other particle and further from the other. You could think about this also as, say, kids sitting on a seesaw or a teeter-totter, I guess depending on where you're from, what you'd call that. So the center of mass here would be the ideal place to put the pivot point so that the 2 kids, even though one of them has twice as much mass as the other, the 2 kids balance each other. Okay, it's the same sort of setup. And so we will see, we'll talk about problems like that where we're trying to balance things in several chapters from now. Well, I guess 2 chapters from now. We'll come back to this kind of idea, that the ideal place to balance it would be the center of mass. Okay, so I'll see you in the next video.